All right, this unit is a really fun unit in calculus, and we're going to talk about extrema, how to find them, how to apply what we know. This has lots of applications outside of the mathematics classroom. First thing, let's just use a little common sense. I know we don't do that very often. Suppose I have a function, and it's defined between these points A and B. It doesn't make any sense to discuss a function that's not defined. And suppose I'm looking for the extreme values of this. What do you think I mean? Well, yeah, it's going to be the maximum values. So if I come up here, what is my maximum value? Well, of course, it's going to be right here. Let me just call that point right there C. Now, this is like at the top of the mountain or the top of a hill. So, basically, we're up here. And we're looking down on the rest of the function. What do I mean by that? I mean the functional value at C has got to be greater than or equal to all of the other functional values. And this is our, what did we call it? Maximum. Now suppose I move my C over here. So that now C corresponds to this point right here. This is the lowest value. This is a minimum, bottom of a valley. And now this functional value of C is less than or equal to all of the other functional values on the interval. Now that equal part is very important, so hang on to it. Now, write down the actual definition of extrema in your notebook. You need to make sure you include that f has to be defined on the interval containing C, and then fc is a maximum when fc is less than or equal to f, and fc is a minimum when fc is less than or equal to f, and it's a maximum when fc is greater than or equal to f on all x and I. Now, here we go. Look at these and tell me if you can find the relative max and relative mins of these three functions. They're very close to the same thing, but they're not the same thing. All right, now let's talk about the extreme value theorem. We are lazy in math, so we will abbreviate this EVT. As a matter of fact, on a problem, if you need to cite the extreme value theorem, you can actually write EVT after you've written it once on your paper. Now, the extreme value theorem says, suppose I have a function f that's continuous on a closed interval. And let's make that interval, in this case, from A to B. Okay, so this is my closed interval. Then f has both a minimum and a maximum on that interval. And lo and behold, for a line, it's very easy to read off what those mins and maxes are. If we come over to a function like this, it's not necessarily so clear, or it's not necessarily, just right there. If we look at this, clearly there is a maximum here and a minimum here. The extreme value theorem doesn't tell you what the value is. It merely tells you it exists. Now, is it possible for the max or the min to be an endpoint? Well, of course. Suppose we go, let's go from this point right here to, let's go to this point right here. All right. Then the minimum on this interval is here, and the maximum is at our endpoint. So you need to make sure you check your endpoints when you're doing the extreme value theorem, because this is a closed interval. Now, we're going to define relative extrema. If there is an open interval containing C, on which C is a maximum, then FC is a relative max. Or you can say that F has a relative maximum at this point. Right? Please write these down, put them in your notebook. definitions always wind up showing up on tests and quizzes, you know. Now, if there's an open interval containing C, in which C is a minimum, then FC is a minimum value, or you can say it has a relative minimum at C, F of C. So it has a relative minimum at x equals 2, or it has a relative minimum value at 2, negative 4. Now again, we have the hill and valley. Hills are relative maximums. Valleys are relative minimums. Now we're going to do something really fun. We are going to find the derivatives at relative extrema. Now, we're not going to worry about finding the relative extrema at this point in time. We're just going to find the derivative at the point for this one, 3, 2. All right. So first thing we need to do is find the derivative. So f prime, oh, sorry about that, of x is equal to, all right, this is a quotient, so it's x cubed times 9 times the derivative of this mess, which is 2x minus 9 x squared minus 3 times the derivative of the denominator, which is 3x squared, divided by the denominator squared. You know what? That quotient rule never goes away. There are other ways we could have done this, but this one works pretty well. Now let's multiply this mess out. 9 times 2 is 18, x to the 4th, minus, let's see, 9 times 3 is 27, x to the 4th, minus and minus, so it's going to be plus. 9 times 3 is 27, times 3 is 81, and that's x squared, divided by x to the 6th. Okay, God, this is ugly. Let's do a little simplification. All right, 18 minus 27 is, oh, negative 9. So let's do 81 x squared minus 9x to the 4th divided by x to the 6th. Let me factor on 9x squared because I can. So this is 9 minus x squared divided by x squared, x to the 4th. All right. Okay, so this is 9 times 9 minus x squared divided by x to the 4th. Now we want to evaluate it when x is 3. What is the value when x equals 3? So I'm going to change my pen color. And I don't have to worry about my denominator being 0. You kind of always have to check that. But when x is 3, okay, f prime at 3 is what? 9 times 9 minus 3 squared divided by 3 to the 4th for 0. All that work. Oh, that was simple. Easy answer. Let's try another one. Let's find the derivative of sine of x at pi over 2 and 1. Okay. So that's right there. Well, g prime of x, derivative of sine is cosine, and g prime at pi over 2 is cosine pi over 2, 0. Okay, that's interesting. Let's keep going. Okay, find the derivative at 1, 0. Okay, this one we've got for x greater than 1, g of x is equal to x minus 1. So g prime of x is 1. For x less than 1, g of x is 1 minus x. So g prime of x is negative 1. Ooh, these two do not equal. Therefore, this is not differentiable at that point. Okay, your turn. Do these in your notebook. When you're done, finish the rest of your homework.